Alrighty, today we're talking about gas laws and the three gas laws and then the combined gas laws. So the reason we study gas laws is to see how the gas is behaving, and within that we're looking at the pressure, volume, and temperature. I realize that you guys cannot see any of this, but this is also on my website, so if you guys would like to get the PowerPoint on my website, go ahead and click that and you can look at this. One thing that I am going to be pointing out on this slide is standard temperature and pressure. The standard temperature and pressure is kind of just a reference point, and you'll see STP a lot in questions. And what's that saying is that the atmosphere is going to be 1 atmosphere, and then we're also going to have 273 Kelvin. Now remember that Kelvin is the measurement of the average kinetic motion. So at 0 Kelvin, we have no motion within our molecules. Alright, so let's go ahead and get started looking at some of these gas laws. First one is the pressure volume, also known as Boyle's law. Now you don't have to know Boyle's law exactly. You don't have to know that it's Boyle who came up with this, but you do need to know what happens when we increase pressure, what happens to the volume, etc. You need to know the relationship. And this relationship is inversely proportional. So what that means is that when pressure increases, the volume will decrease. So if we have a decrease in the volume, we're going to have an increase in the pressure, inversely proportional. Now, when you think about this, this makes sense. If we take a gas, put it in a balloon, and all of a sudden we shrink that balloon, remember temperature staying constant, the pressure, so the amount of force that the particles run into the side of the balloon is going to be increased. So just know that they are inversely proportional. The next one is Charles' law. So Charles' law is looking at volume and temperature. And these are directly proportional. So when temperature increases, the volume is going to increase as well. When temperature decreases, the volume is going to decrease. So this is kind of, think about the average kinetic motion again. Think about the motion of the particles. When they're moving faster, they're going to take up more space. They're going to want to take up more space. And for this, our pressures remain constant in Charles's law, the volume temperature. The next one, Gay-Lussac's law. He looked at the relationship between pressure and temperature. And what he found is that when gas is held at constant volume, so when volume's not changing, that the pressure and temperature are directly proportional. So if temperature is going to increase, so will pressure. So let's do some problems with this and actually look at the math behind it of what's happening. So when we combine all these gas laws, we get this equation. P1 times V1 over T1 equals P2 times V2 over T2. So this is our combined gas law. This is also on page 3 in your reference tables. So on test day, when you guys get your reference table, you guys know where to look, and that is right there. Alright, let's do a problem. So, a gas occupies 12.3 liters at a pressure of 40 millimeters of mercury. What is the volume when the pressure is increased to 60 millimeters of mercury? Now, before we actually do any math, let's talk about what we should happen using the pressure volume. So, we know the initial volume and the initial pressure, and then we know the final pressure. So we're trying to figure out the volume. So what you should look at is the pressure. Now we know that the pressure increased from 40 to 60. Now, think back to the volume pressure law, and you guys should remember that they're inversely proportional. So if volume increases, if pressure increases, like this problem does, pressure increases, then the volume should drop. So we should see a decrease in the volume. So let's see if that's true. So we're going to set up our equation. P1 V1 over T1 equals P2 times V2 over T2. Now notice that nothing is said about temperature in this problem. So we're going to assume that it's constant. So we can basically go ahead and just get rid of temperature. We're not going to deal with temperature at all because it is held constant. So now let's write down our given. First thing we're given is our volume 1 of 12.3 liters. Next, we're giving our pressure, our initial pressure of 40.0 millimeters of mercury. We go over to our P2 and V2. Our V2s are unknown, that's our X, that's what we're trying to figure out. And our P2 is 60 millimeters of mercury. Now we can plug this into the equation and solve. So let's plug it in. So we have 12.3 liters times 40.0 millimeters mercury equals our millimeters of mercury, 60. Alright, small, times X. Times are unknown. So now we're just left with math. We have to solve for X. I'm going to move the camera over a little bit. I'm going to make this X right here so that you guys can see it. So I'm taking off the units. You guys will need the units though. I'm just doing this to save some space for us. So let's figure it out. So first thing we have to do, 12.3 times 40.0. That gives us 492. 492 equals 60x. Divide both sides by 60. Those cancel out. 492 divided by 60, and that gives us 8.2 liters equals X. Don't forget your units. It's very important that you guys have your units. Alright, let's do one more, and that makes sense because we predicted that the pressure increased and the volume is going to decrease. So that goes with what we're talking about. Let's do one more, and then you can do some on your own. Alright, so 2.0 liters of gas is collected at 25 degrees Celsius and 745 millimeters of mercury. What is the volume at STP? Now remember, STP stands for standard temperature and pressure. So let's go through and write down what we're given. So P1, V1, and T1. P2, V2, T2. So the first pressure that we come across is 745 millimeters of mercury. Our volume, our initial volume is 2.0 liters. And our temperature is to 25 degrees Celsius. Now remember, we have to change everything to Kelvin. So we're going to change 25 degrees Celsius to Kelvin by adding 273, and that gives us 298 Kelvin. And to figure that, whenever we're converting Celsius to Kelvin, we're just gonna add 273. So let's write our P2, V2, and T2. So what is the volume? So that's our X, that's our unknown. Then we have P2. Now we have, in the question it says STP, standard temperature and pressure. So if you look at your reference packet, it gives us the standard temperature and pressure. So right there is our standard temp, and our standard pressure is right there. So our standard pressure is 760 millimeters of mercury, and our standard temperature is 273 Kelvin. So now we can set it up in the combined gas law equation. So I'm going to switch to red. I'm also going to drop the units for the sake of space, and I'm going to move the camera over so you guys can see it a little bit better. All right, here we go. 750 times our volume times 2 over our temperature. Our temperature is 298 at the beginning, equals our standard pressure, 760, times our unknown, our X, what is the volume, over our standard temperature, 273 Kelvin. Now we just plug it into the calculator and solve for X. So 750 times 2 divided by 298 gives us 5.03 equals 760 X divided by 273. Multiply both sides by 273. 273 cancels that out, times 273. That gives us 1,374 equals 760 X. Divide both sides by 760. This is just math. Divide by 760 equals 1.808. So you guys should be following along with your calculator, hopefully. And we know that X equals 1.81 for rounding. Now we have to do our units. I guess it stopped. Now, the units. The units will not change because we're finding the second volume. Our units from the first volume is liters. So our second one is 1.81 liters. And there is our final answer. That is how you do a combined gas law problem.